you, Jamie. Thanks everyone for coming in and for your interest in these 300 pages, or as Jamie put it, 1,000 pages that I recently posted. So I have good news and bad news. So the bad news are that there's no way I'm going to go through any order one fraction of these recent papers that I published. So it's going to be necessarily a very shallow overview and with maybe a few dips into the more technical waters. The good news is that I'm happy to talk more about this, and especially when travel reopens, I would be very happy to spend some time discussing this with anyone who is willing to learn more in person or even online if necessary. So please feel free to ask me questions now or after the talk, and if this grabs your attention, I'm very happy to organize some way of going over more details later. So you can see the title, and you can see the papers from which this talk is based. So let me start by just giving a very broad overview of the ideas that are relevant here and the question that I was trying to address. So when we talk about QFT, different people can mean different things, but if you look at the whole of literature, you can sort of identify two extreme idealized versions of what QFT might mean. And I'm going to describe them now very briefly. So one extreme, one ideal version of a QFT is what you might call a continuum QFT, where essentially a continuum QFT is some machine which takes some nice manifold, smooth with some nice structure on it, maybe with some marked points, and spits out various numbers which you can then relate to probabilities of various physical processes. So basically, you can just think of QFT as some machine that assigns some rich set of interdependent functions that are labeled by positions, momenta, representations of various groups, and so on. Based on these labels, gives you some amplitudes or other physically interesting observables or quantities. Essentially, everything is finite, and you just never, you never necessarily ask for the nuts and bolts of how this works. This is a very bootstrappy kind of philosophy, but ultimately, this is what you also learn in from Peskin and Schroeder, or from other introductory textbooks. You just learn baby examples of this. Now, on the other hand, on the other extreme, you have something that I will call lattice quantum field theory. And here I'll be very extreme, like more extreme than most people are. So by lattice, I will mean that the system is completely finite dimensional, that the Hilbert space is completely finite dimensional. So it's a quantum theory of the kind that you will learn in your Griffiths undergrad course or something, with a possibly exponentially large Hilbert space, but finite, and with all of physics encoded in this one Hermitian matrix called the Hamiltonian. So if you can diagonalize it, you know everything about the system. So these are two maximally separated views of what quantum field theory might be. And the question that I want to pose is, to what extent is one a good approximation of the other? Or rather, to what extent are they describing the same object? And under what conditions are they describing the same object? Now, this is an old question, and a lot of thought has gone into various versions of it. So the question itself is not new, of course. Possibly the main set of ideas that are relevant to this question came in the 60s and 70s from people like Wilson, Kadanoff, other people like other statistical mechanics people, and who realized that there's this deep connection between various theories, especially near phase transitions. So there was this intuition that lattice systems that you may see in a lab or something will in the end be nicely describable by these continuum field theories, and that there's some notion of universality there that says that you will always end up getting similarly behaved amplitudes that similarly behave 2-point, 3-point functions with similar amounts of symmetry and so on. So this is great. This is absolutely amazing. Except it wasn't a very precise correspondence in the grand scheme of things. And what I mean by this is that this correspondence said a lot about what happens in at sort of the lowest energies, or when you're interested in few point correlators, but it sort of didn't capture the entire structure of your quantum theory. It didn't say much about how these things broke down, other than that they had to somehow break down, and in general it was there were many questions that are still unclear. And even today, there are certain signs that a precise correspondence might actually be impossible. And I've listed some of them. Like, none of them are insurmountable obstacles, but they are all signs that sort of make people wary about using lattices to describe continuum theories, for instance. So already in the 80s, we knew that putting some fermionic theories on a lattice was difficult. And in fact, there are certain no-go theorems saying that it may be impossible to do them and preserve some other features which we may like. Another statement that people often make is that lattice theories, unlike continuum theories, do not have this feature of an infinite amount of entanglement at short distances. Or in other words, that continuum Hilbert spaces cannot possibly factorize the same way that lattice Hilbert spaces do into a product of direct product of smaller Hilbert spaces. Another way to phrase it is to say that there's no meaningful OP structure that you can put directly on a lattice, because your two operators are either on the same site or not, and there's no notion of bringing them close together and replacing them with a third one. At least naively, it looks like that. So that's yet another point against this asking such questions about such correspondences. And the third point that I want to stress is that we actually really do lack many models for many interesting continuum theories, starting with Einstein gravity. We generally lack a lot of nice models, nice lattice models, which in an obvious way reproduce the continuum results. So, the lack of such models kind of suggests that maybe they don't exist, or they do exist and there's something very sketchy about them or something like that. So that's sort of discouraging. But then there are also signs that the correspondence like this really has to exist. One sign, which again, these are not theorems, these are not necessary conditions or something, but things that are good to keep in mind. One sign that especially high energy physicists might like is the fact that even continuum field theories have things like entropy bounds. So you really should not exist that you can have an infinite dimensional Hilbert space in a finite volume of space, because that would signal trouble if one's gravity is included. Another thing that you can say is that, well, we may not know how to put various theories like Chern-Simons or various other continuum theories of interest on a lattice, but we definitely do see them arising from lattice systems. So maybe the problem is indeed that we are not thinking about this in the right way, about this correspondence. So the way I see it is something has to give. There should either be a more precise way to formulate this correspondence, or there should be a more precise statement about why it cannot exist. And what I want to argue in this talk is that, and what I argue in my papers and derive in significant detail, is that the correspondence actually exists and can be made quite precise. So,
could I ask a question? So you're kind of mixing in it seems to me to be a separate issue here. If I want to describe continuum non-gravitational field theories in this way, and versus asking whether there's some lattice model of gravitational field theory. I mean, it seems like those are two separate claims. So are you going to suggest that even gravitational or like UV complete gravitational theories have some underlying lattice description?
Well, I do not have any calculations to bear that out, so I will not claim that specific thing, but let's just say that I have a firm religious belief that that would be the case. But that this is not part of the paper of this talk. Gravity, I'm just using it as a motivator here, and for now I'm not claiming anything about it. Now, if we believe in things like holography, then you can say that I am claiming that gravity has an underlying lattice structure, because I'm going to end up claiming that things like n=4 or other CFTs will have underlying lattice structures.
I see. So your lattice.
Yeah.
Oh, sorry, there's an echo, but so in that case, you're not assuming the lattice geometry is related to the bulk geometry.
Yeah, like I'm not saying anything about that yet. I'm basically just for now everything I will want to claim, everything that I want to defend in this paper, in this talk, will be about quantum field theories, and I will actually stick to 2+1 dimensions or lower. The methods I will talk about will work in higher dimensions. I just haven't worked them out yet. So let me.
Okay, so
let me just say that this is the realm in which I will actually defend my statements and provide details on how these things work. But I have a very strong belief that things will generalize in nice ways, and with a sufficient amount of work put in, and that similar statements may one day during our lifetime be made for gravity as well. Let me unless something very unexpected happens.
Okay, but the answer for gravity might be that the description is a lattice version of a holographic dual of the gravity theory.
Yeah, I mean, in the end, like it might turn out that the right way to think about the gravity side will be, in terms of some fixed pre-geometry, if you will, in which, you have some other degrees of freedom which serve as, your dynamical geometric fields, your dynamical lattice fields. But I do not. I'm agnostic about that. It's an option.
Okay.
Yeah. Okay. So the key idea, the key ingredient in this, in developing the correspondence, is something that I will call smoothing. It's essentially a procedure that very explicitly shows you how you can go from a lattice system and somehow extract from it a continuum system, or a system that still lives on the lattice but behaves in all ways like a continuum system up to some desired precision. In this sense, it's very similar to an RG transformation. Not quite the same, as you may see later, but intuitively, very intuitively, you can think of it as some kind of decimation or some kind of reduction, which takes some nice theory where some nice lattice theory where your Hilbert space is a nice direct product over many sites, and returns something where such nice product structure is gone, and in particular your fields and your operators actually very smoothly across your spatial manifold or space-time manifold. And this fact that you basically reduce down to just smoothly varying fields is essentially the only thing you need to do in order to extract the continuum-like degrees of freedom. And it's kind of interesting that you can actually do it pretty explicitly in many, many examples. So the main benefit of this entire story is the fact that it allows you to be very precise about what you mean by a continuum QFT. Now you can actually put essentially all aspects of it on a lattice and understand how various continuum notions break down as you go to higher energies or higher or shorter distances. In particular, one thing that I want to stress is that there will be a hierarchy of cutoffs. There will not be just a single thing that you may call the lattice spacing. There will actually be several cutoffs involved in this definition, in this notion of smoothing, and these these cutoffs will then and their ratios will then figure non-trivially in various bounds that you may put on various observables. Like, to take one random example, if you want to ask yourself, okay, I have some winding configurations or instantons in my system. What's the largest instanton number, or what's the largest winding number I can have in the system? That will depend in some non-trivial way on not just the lattice spacing, but also on these other cutoffs that will come in. I will not derive this in this talk, but it's even just a side note in my papers. But you can actually talk about such precise statements.
Can I ask a question?
Of course.
And you should feel free to not answer me now if you get into more detail later. But there's work mainly by Toby Cubitt and others on undecidability of the spectral gap and undecidability of phase diagrams and so on, which I think of as sort of a statement that there is no such thing as a continuum limit for a general lattice theory, because these are examples of things where you can take the theory arbitrarily large and it will change from being gapless to gapped or vice versa. And they've, if you don't know about this, then maybe this is not a useful question to ask, but I wonder if that sort of lines of argument seems to contradict or be in tension with the notion of being able to extract a continuum theory for a lattice one. And I wonder if you have anything you can say about that.
So I can't say anything too precise because I am very far from a computer scientist, and these questions of decidability and so on are not my métier. So I may not have anything useful to say about this.
Okay.
I am aware of these papers, but yeah, I think they're just asking, that's asking separate kinds of questions. That's asking things about that are closer to efficiency or something like that. Unless I'm very much mistaken.
Yeah, well, I mean, maybe I could just say why I think it's related. I mean, basically, so, yeah, so it's a CS question. Basically, the reason it works is you can map it to the halting problem. But the upshot here is you can always construct theories such that for some number n, the theory behaves totally differently when you go from below n lattice sites to above n lattice sites. And so this seems like basically this seems to imply that taking the continuum limit can't be
I mean,
there can always be
okay,
obstacles
let me just say very quickly that I think that number n is some extra input that you put in based on some other criteria. And right now I don't, I personally do not have that kind of cutoff.
So your way of taking the continuum limit doesn't involve taking an infinite number of lattice sites.
I mean, it involves there being a large number of lattice sites, but the number is, the number is large, but ultimately finite. And, I will have 1 over n corrections and all of those things. So, but yeah, we can maybe talk about this later because it's definitely not going to be something I'm going to talk about more.
Okay.
Don't have anything meaningful to say. So, yeah. Okay, but to be honest, the main shortcoming of this entire story is that I will not be able to tell you an efficient way to actually solve a given lattice theory by reducing it to some nice universal free or almost free EFT or something like that. So if it's interacting, you'll have to use your normal Wilsonian RG and other methods to solve it. What I'm going to essentially say is that if you solve it or by some other way figure out that it has some nice structure that I'm going to make explicit in the next slides, then that nice structure will imply a continuum, will imply an explicit construction of a continuum limit. And it's extreme. And for most intents and purposes, you don't you will work self-consistently. You will not be able to solve to exactly diagonalize your starting Hamiltonian and figure out whether your theory actually obeys the conditions for there being a continuum limit, but you will assume it does, and then you will work self-consistently and see that nothing terrible happens. And that's sort of the name of the game in theory. And at least for us physicists, I think that's fairly reasonable. And if this was too fast, then you will see in a second what exactly that means. But so because I will not be able to go through all the results and all the various things that I was able to confirm or derive from the lattice, so here is just a short list of things you may call highlights that I'm going to go through it, say a sentence or two about each of them, just to give you an idea, an appetizer, and maybe point you towards different parts of my series so far. So the main thing is this formal definition of the smoothing procedure and therefore of continuum QFTs in terms of some lattice models that are on large but ultimately finite lattices. That's what I'm going to talk about in for the rest of the talk. It has a bunch of applications, and you can apply to define various different QFTs. If you apply it to let's say these ZK clock models, or things you might call quantum rotor models in 1+1 dimension, or XY models if you're a statistical mechanics person, you actually get some interesting new perspectives on it. For instance, you realize that this line of critical points, the BKT regime, is really composed of a series of intervals with different subgroups of this ZK being broken. So basically, you can think of this line of critical points as a cascade of symmetry breakings. That and this would all be sort of invisible if you just took k to infinity and the lattice spacing to 0 very naively. But you can sort of resolve it in this nice way, and you also get an idea of how the Mermin-Wagner theorem breaks down and allows this kind of thing to happen. So that's one set of things that you can do. And in this line of critical points, you can of course then compute various interesting things like operator product expansions of vertex operators directly from the lattice data, and other similar things. Another thing that you can do is once you recast everything in terms of path integrals, it turns out that Noether's theorem no longer cares whether your symmetry is discrete or continuous. They're kind of on an equal footing, and the same procedure can be used to prove Noether's theorem for both discrete and continuous symmetries, which is good because I was always bothered by the fact that that theorem distinguished between the two, because what's the difference between a continuous symmetry and a Z-million symmetry, or like say a finite but large order symmetry? And the answer is there's no difference, and this sort of makes it clear how to put them all in the same framework. Unfortunately, this doesn't give you new interesting Noether charges, but it's nice to know that there is a unified framework. Another thing which I may talk about if there is time, which there probably won't be, is the fact that this gives you a very nice view on like the origin of both contact and counter terms in field theories, in partition functions or generating functionals. So for instance, if you have massive fermions, you can actually very clearly see in what sense in a completely discrete setup you get an induced Chern-Simons term, and which is nice. It's one way you might go about putting Chern-Simons on a lattice. It's not the most elegant way, but it's definitely nice to have a lattice mechanism for this. Then you can also derive various dualities, various IR dualities that we all know and love, like bosonization in 1+1 dimensions, or T-duality in 1+1 dimensions, or particle-vortex duality in 2+1 dimensions, and so on. You can derive them exactly from the lattice and point out which operators fail to obey them or fail to map under them, and which do not, using these cutoffs that you've introduced in the previous in the definition of smoothing. You can make statements about how supersymmetry works on the lattice in ways that, at least at a level of precision that I have not seen before. You can discover new global anomalies by trying to gauge continuous symmetries of these ultimately finite systems, and so on. So there's a lot of stuff happening. I will, as I said, not be able to talk about all of them. So what I will certainly talk about is this. If we are lucky, I will say something about this. And we will certainly not be lucky, but I can maybe scroll down and show you the slides for this. And for the rest, I will definitely have to talk to you at a different time. So, okay, this is the end of the broad overview. And if you're confused or desperate for details, that's good, because I'm going to start diving into some more formal things. But if you have any general complaints or comments at this point, I'm happy to take a minute or two to answer them.
So are your lattice are your lattice theories generally quantum theories or classical theories?
Oh, excellent. So this is going to be the first part of my next slide. They're quantum theories. They're all in a canonical formalism with an explicit Hamiltonian, all on a t=0 time slice, and evolving, if you will, just by conjugation by e to the iht.
So it's like you took a continuum field theory and put it on a lattice, in a sense.
Well,
so as distinct from studying the Ising model or something, which is completely classical.
Yeah, in fact, the Ising model, or precisely deriving things like the OP coefficients for the Ising model, is something that I did as a sort of warm up for this, and that is a paper that I actually published in 2019. But yeah, that was sort of the first thing I did, and this is sort of generalizing it to all possible target spaces, or at least the Abelian ones, and so on. But yeah. Good. Okay, so let me start with the sort of formal definition here. It's going to be a little bit dry, but I will try to keep it palatable. So, as I said, the context in which I will work is going to be just canonical formalism. So continuous time, or rather, I'm not even committing myself to saying anything about time. I'm just on a single time slice. But everything else is discrete. So position space and target space are discrete. Everything is explicitly regulated. And the total Hilbert space dimension is, as I said, finite. Everything I said can be recast in terms of path integrals. And I optimistically said later, possibly a different talk, but it's certainly in the papers and so on. But it's sort of conceptually clear to start with the canonical formalism. So the main thing is to define an operation that I call smoothing, which acts on operator algebras. So it's a very general framework. So if you start from some lattice theory whose operator algebra is just some possibly subalgebra of complex matrices of finite size D. And this is going to be some if this algebra, or rather if this theory, the algebra plus the Hamiltonian, obeys certain requirements that I will spell out, then you can perform this procedure and reduce to a subalgebra called AS, which obeys some very nice, whose elements obey some very nice criteria. So there are two properties that this starting algebra has to obey. I've listed them here. One is these words don't really mean anything to you, so I will explain them in the next slide. But basically, it has to have something that I call a pre-continuum basis. So there has to be some natural structure of the algebra with respect to the Hamiltonian, and the Hamiltonian also has to give you a nice notion of a momentum space with some natural topology on it, with some natural notion of adjacency on the momentum space. So I will describe that in detail later. And let me just emphasize that what this procedure ends up giving you is another lattice theory, where, as I said, all the fields very smoothly, both in the target, if the target is large, and in the spatial manifold, and the proximity to the continuum, the quality of how continuous things are, is not governed by the size of the lattice spacing, or in other words, by the size of the lattice, by the number of sites on the lattice, but is actually governed by another cutoff, which is going to be introduced during this procedure. So, so there is a separate cutoff, which is not the same as the lattice spacing, which governs the continuum behavior. This has been known in very cryptic ways for more than 50 years. I think the clearest statement of this is in Duncan Haldane's paper on Lattinger models, on Lattinger liquids in like 81 or 82 or something, where he said that there has to be a second cutoff, which is in no way the lattice spacing, and that's crucial for getting the right bosonization properties and stuff like that. But he kind of didn't take the next logical step and put it in the context of generally defining QFTs, continuum QFTs. But the ideas have been floating around for a long time. So let me explain what this means. So the first statement that I want, the first condition that my starting algebra on the lattice needs to satisfy is that it has this thing called the pre-continuum basis. This is a kind of generalization of a Fock space. So basically, I want there to exist a complete set of commuting operators nk, where k is some label, and the set of all labels k is what I will call the momentum space. At this point, it's just some set of labels. They don't have any useful values or anything. And these operators nk, I will call particle numbers, and essentially they're operators that are all symmetries of the Hamiltonian, and they all commute with each other and are normalized in such a way that they take integer eigenvalues, as you see here. So basically, for each momentum mode, I have a finite number of particles I can put into that momentum mode. This number is this integer jk. And this is not the Fock space construction because these jk's can all differ. I'm not assuming anything about the statistics of these particles or anything like that. I'm just saying that these things have to exist. And almost all theories of interest will have at least a pre-continuum basis. So this is not a huge requirement yet. But some theories are going to be pathological and not have it. Like a generic lattice theory, if you just take a random matrix, will not have it. And the algebra A that I will start with is going to be generated by ladder operators. So operators that just increase or that create or destroy particles at each momentum k. These may or may not commute with each other. I'm not assuming anything about that. When I say that they generate the algebra, I mean that if you take all of their possible products, and then all the linear combinations of these products, you will get all possible operators in the algebra A. That's what generating means in this context. So this is the first assumption. And it's essentially something like saying that the theory is integrable or at least approximately integrable. And that's sort of not an accident. Basically, the crux of what I'm saying here is that to get something that's like a continuum theory, your underlying lattice theory has to be close to integrability. That may sound strange, but remember that the modern point of view is that to get something close to continuum description, you need to be close to a conformal fixed point, or at least a scale invariant fixed point. I'm kind of saying that the really important thing is really the existence of these conserved numbers nk that may or may not later give rise to a conformal structure. Good. So that's step one, and then step two is to say that the Hamiltonian also needs to be nice enough that it generates some nice structure on the momentum space. And so let me explain this, because this is not obvious, and it took me a while to find the right way to phrase this, or at least the correct, the logically consistent way to phrase this. So assuming that there is a pre-continuum basis, any Hamiltonian which has it can be written as some polynomial in these nks with some coefficients which I call hk, little hk. The important things, like sort of the most important coefficients for all practical purposes in all models I know of, are the coefficients that I will call dispersions, that are just next to these nks, the individual nk operators in the Hamiltonian. There is no reason why these dispersions in a generic theory would be smaller than all these other coefficients or other stuff that appears here. But it turns out that if this is the case, then you can naturally order your momenta just by looking at the value of hk, hk1 rather. You can order your momenta such that nearby points on the lattice correspond to excitations of similar energies. So basically, by having this, you can use this nice energy, this nice set of dispersions to put a lattice structure or a topology on your momentum space. This is just the number of sites on the lattice between points k and point L, and this is some general notion of uniform continuity that you can put on the lattice. So the assumption is that there is some structure that the Hamiltonian induces, and this is sort of the natural way to do this, by saying that the dispersions are much greater than all these other coefficients here. This is essentially saying that the theory is close to being free. These guys are, things that you will induce by turning on various interactions in the theory. So a generic theory will, of course, not be too close to this, and then it's a question of, universality. You might need to do some Wilsonian RG to reduce the number of k's until it's closer to a fixed point or something, or to a free point, or something like that. But in general, I will assume that for some reason or another, the Hamiltonian induces a natural structure like this, and that means that I can associate, that I can define. It's meaningful to talk about the low energy subspace of my momentum space. So that means that I can talk about a set of momenta, which I will call PS, S for smooth, that are associated to low energy excitations in the theory. This set PS may be disconnected. That will correspond to various different flavors or various different species of particles at low momenta, or something like that. But the important thing is that the low energy subspace is going to be robust under small perturbations. This is essentially why I phrased everything this way, because I'm still allowing myself that these HKs, these higher HKs, are going to be non-zero, but at least small enough that they do not ruin the general fact that low energies correspond to small distances between momenta. If this is the case, then I will be able to define the smoothing procedure, as you will see on the next slide. And the smoothing parameter, essentially the thing that will control the closeness to my continuum limit, will be this ratio, the relative size of this low momentum or low energy subset compared to the entire system. So you can think of this size P as setting your lattice spacing, or the number of different modes that you have in your system, and this ratio as setting the number of as setting sort of as controlling the derivative expansion. So in my 2019 papers, I sort of cockily call this thing, the string scale, this ratio, because it essentially does the same thing that string scale does in space-time. It controls the derivative expansions in some effective field theory. But yeah, it's obviously not exactly the same. So that's the formal stuff. So those are the formal ingredients. So all I want you to remember is that there are these two formal ingredients that a lattice theory needs to satisfy. And then once you have those, you're good to go. And then you can define the following smooth algebra in this way. So for all momenta in the small momentum subspace in PS, just take all the operators, all the ladder operators, all their products, and so on. So don't do anything at low momenta. Whereas at high momenta, I want you to discard all the ladder operators, but keep the particle number operators. That's the unusual thing. If you were totally Wilsonian, you would just sort of integrate out everything above some momentum k, and just find some effective field theory for this. Here I'm telling you, well, you may do that and find effective field theories, but I'm also saying that once you have found a theory which induces this nice structure on the momentum space, now do this projection. So project all of your operators to this smooth subalgebra. These guys now commute with everything else, these NKs, because there are no ladder operators that can fail to commute with them. And so that means that every state, with every density matrix that's in the smooth subalgebra, that still remains pure after smoothing, every such state will essentially have a fixed pattern of short distance entanglement, which can, the entanglement entropy, the entropy from the entanglement at short distances or large momenta can grow with the system size. So in that sense, it can be infinite. But the point is, it's fixed. You don't have any entanglement transfer from high momenta to low momenta. This is sort of, but you can still quantify what your particles are doing, even at these low momenta. Even at these high momenta. It's a bit of an unusual structure, perhaps, so it'll take some time to get used to it, but it's kind of clear what it does. And then, meanwhile, these operators CK, which only exist in momentum modes in PS, you can then Fourier transform them, as I've written here. So you can define some space, some lattice M star, which is sort of the Fourier dual, or some people might call it the Pontryagin dual of P. And basically, you can use this Fourier transform to exchange these momentum operators CK with fields C of X, which all happen to obey a smoothness constraint like this. So they all vary smoothly from lattice side to lattice side. And the difference between them is constrained to be some operator of size PS over P. So this is sort of what forces all of your fields to be smoothly varying, and that's sort of the possibly main hallmark of what we normally call a continuum QFT. So that's sort of the formal statement. And I will only make one more formal statement, and then I'll give examples, because this is possibly unfamiliar. The main thing I want to stress is that, so I've defined a projection called smoothing, and that projection does not commute with taking operator products. So if you have two operators, so let's say an operator OX and an operator O tilde Y, defined on your original lattice, you have two options for what you mean by a smooth operator product of them. You can first multiply them and then project, or you can first project and then multiply. the order of these operations matters, and the difference between the two, sort of the commutator between the two operations, is what you may call an operator product expansion. It essentially encodes the most singular stuff that happens when these two operators are brought together. To see why the product does not commute with smoothing, just realize that this operator here can contain something like some operator of the form ck, and this operator can contain some operator of the form ck dagger for some momentum k that's not in PS. So individually smoothing this guy would just remove this ck. Individually smoothing this guy would just remove this ck dagger. But if you first take their product, then they together will form ck dagger ck, which is just nk, which does survive the smoothing. So basically these high momentum, so basically this guy here, this difference precisely contains the data on nk at k not in PS. I guess this is what I wrote here. So so this is going to sort of be the, and this is everything here is defined directly on the lattice, just with this one explicit cutoff. And once you then apply this philosophy to various different theories, you will end up getting precisely the familiar OPE coefficients and so on, which I've done for simple 1+1 theories in 1+1 dimensional theories in 2019, and then I did it again for more complicated scalar and gauge theories in this series of papers. Okay, so that's the formal stuff. I would spend the rest of the talk just giving or scrolling through a simple example or two, but let me stop now and ask for questions first, because I assume there might be some.
Should I think of the fixed pattern of high momentum entanglement as just sort of equivalent to like the usual assumption we make when we do RG flow, that like the UV modes we're integrating out are in their vacuum state?
Yes. So yeah, essentially yes. So when I say that, right. So because these operators are in the center, you can think of the Hilbert space, or the remaining, you can think of the remaining Hilbert space as being split into super selection sectors labeled by the values of these NKs. And your overall vacuum will belong to one of these sectors. So indeed, if you just focus on that one sector, then you are sort of assuming a particular population of high energy modes in the vacuum. But this also tells you how to do this scenario in all the other sectors as well.
Okay,
so
great.
So for instance, if you have a fermion theory, these NKs will, in a fermion theory, these NKs typically are given by something like theta of minus k or something like that. So you get a Dirac C. So it's either 0 or 1, depending on the sign of k. Whereas for bosons, this might just be 0. And for other theories, it might be something else. Or like if you have a very massive theory, then this will depend on your mass or your Fermi momentum or something like that. So all of those situations will be covered in this, and basically changing the depth of your Dirac C or whatever will correspond to just changing the super selection sector in which you will work.
Thanks.
So it's very similar to Wilsonian RG, but it sort of makes it explicit. Keeping these guys makes it explicit how you can calculate, how you can not just end up on a coarser lattice with fewer sites. You actually stay on the same lattice, but your fields instead are forced to forget some details of the underlying lattice. Essentially, that's are forced to sort of move slowly on the original lattice. And that's one of the main things that you get. So in particular, This is the example that I had in the previous paper, like not even in this series. So I'm not going to go through this derivation in detail, but essentially all the formulas are here. So you can start from some very explicit Fermion Hamiltonian, which just, you have some spinless fermion, which just hops from side to side, and you start from, and your initial lattice has 2n sides. 2n is just for convenience. You can solve this theory exactly. You can find that the dispersions are given by this as a function of momentum. Like momentum here is just naturally the Fourier dual of the original lattice. And in fact, you will see that there are actually two disconnected regions where the dispersions are small, corresponding to one chirality or another, if you will. That's a very nice feature of 1 + 1 dimensions. And so basically your continuum theory, you can think of it as there being sort of two different fields labeled by whether they live in this area or in this area. So you get two different fermion fields. You can unite them into a single two-component object, a Dirac spinner, and then you can smooth them in the way that I prescribed. So you can essentially just impose another cutoff in the momentum space. So normally these momentum would go all the way to n half in this case, which is the number of lattice sides. Here the momenta go all the way to some number ks, which is much smaller than n. And once you do that, your fermion fields end up, they still live on this lattice of n sides, but they also have to obey these constraints. So it's like you've imposed a specific constraint on all of your fermion fields, that the difference between fermions and nearby sites has to be of this order, ks over n, where ks is this guy. And this is actually really useful because then you can compute various other properties. For instance, if you compute the smoothed fermion currents for each chirality separately, that are defined by this. I won't go into this calculation, but I just want to stress that it is these currents that satisfy the right Kac-Moody algebra with level 1. And not the how should I say, not the microscopic ones, not the ones that you would normally have gotten if you just naively took the fermion density and momentum and Fourier transformed it. That would just give you a trivial Kac-Moody structure. That would not give you a non-trivial any non-trivial answer. So this is the kind of stuff that was known to some extent and was said in various different ways by people in the 60s onwards. But it turns out that this more global way of thinking about it actually applies to all theories, not just to fermions in 1 + 1 dimension. And you can calculate other things in this fermion theory. You can calculate OPEs the way I described. You can then be very clear about how to bosonize these things. I may have talked a bit about this in my talk at UBC just before the pandemic. I think it was an It from Qubit meeting. I think it was at UBC, but yeah. Basically, I talked about something similar back then. But let me actually say something that is completely new instead. So I didn't really say anything about path integrals so far, and I don't really plan to, other than what you see on this slide. But let me give you this example, and then we can adjourn, and you can ask me more questions or so on. So this entire procedure also extends to talking about smooth fields in space-time, if you were to construct your path integral in the usual way. And that smoothing in time actually turns out to be extremely crucial to getting many other results. So I already showed you that smoothing in space was crucial to get, or at least I told you, I didn't show, but I told you that the smoothing in space was crucial to get the Kac-Moody structure. That if you were just working with microscopic quantities, you would not get it. Smoothing in time is also crucial to get other similar structures, which we normally would have a hard time putting on a lattice. Most interestingly, Chern-Simons theory. So I will illustrate this in the cleanest possible way in 0+1 dimensions. So where integrating out massive fermions can be said to generate a one-dimensional Chern-Simons term. So the way this works is very simple. So take the simplest possible theory you can think of, essentially, the massive fermion in 0+1 dimension. So this is actually even simpler than the theories I discussed so far, because there's no notion of spatial manifolds, there's no notion of spatial smoothing, there's nothing. This is literally a two-dimensional Hilbert space. And call this operator J. That's the fermion current, the only fermionic current you have. You can calculate its ground state expectation value, and it can be given by this. So it depends on the sign of the mass in this way. And if you have been calculating Chern-Simons things, you know, in 2+1 dimensions, you know, you're already familiar with how, you know, various things depend on the sign of M, like the induced Chern-Simons level. So not surprising. And now you can ask, okay, so I've gotten this result just by diagonalizing this 2x2 matrix. Not why am I wasting your time with this? Well, the question is how to get this result from a path integral. And that's a very non-trivial question, actually. Or, you know, I can explain it in a few minutes, but it still has a non-trivial idea in it. So to calculate this guy, you can do the standard thing of just, you know, expressing some correlator of fermionic fields by Berezin path integral. There are explicit rules for how to do this. This is an essentially exact formula to first order in m times d tau. Basically, you just introduce many Grassmann variables at different times tau. Tau is the lives on a thermal circle, blah blah blah. And then the crucial step, because this path integral is kind of completely useless. You can't evaluate it in other than numerically, the way it's written. To actually calculate it, you need to assume that your fermionic fields vary smoothly with time. This is not a justified assumption. So instead, the way to precisely phrase this is to say, let us define a new path integral in which I have taken each field eta tau, each Grassmann field eta tau, and just projected it the same way I did in the smoothing case. I just projected it to a configuration in which only some low Matsubara frequencies have been retained. So basically, instead of having up to some number n0 points, n0 is the number of different values of tau along the thermal circle. Instead of having that many frequencies, I just by fiat say, let me consider a new integral in which my Matsubara frequencies are limited by some much smaller number ns. It's a completely ad hoc thing to do, but the resulting object actually varies smoothly with time. And for the same reason that the previous fermionic fields or more general fields varied smoothly with, across space, because essentially they only have low momentum excitations in them. And now I can say, okay, so I have essentially butchered this path integral. I have just replaced everything by these smoothed variables. I have no right to expect that this new path integral will actually give me the right answer, and it doesn't. So interestingly, however, if you compute the path integral of the appropriate, of the smoothed fermion bilinear, note, by the way, that the non-smoothed, the lattice version, is denoted by tau in the index, whereas the smoothed version is denoted by tau in the argument. That's a general convention, which is actually pretty useful to distinguish between the two. So if I calculate the expectation value of the two fermion fields in this smoothed language, as I said, I do not get the answer that I've given you here. I do not get the exact answer, but almost miraculously, as long as the temperature is smaller than some function of this mass, of this cutoff ns, I will actually get this very interesting relation, which is totally not obvious, between the exact result and the one that I've gotten from my butchered path integral, for my temporally smoothed path integral. So proving this, ab initio is difficult. You just essentially compute both sides and see that they always differ by a factor of 1/2. So, which is essentially this factor here. Okay, that happens, and so that tells you that in order to actually use the temporally smoothed path integral to compute the right microscopic correlations of fermions, you actually need to do something more than just temporally smooth. You need to add an extra term to the generating functional, if you will. Basically, this 1/2, you can't change it by changing by adding counter term. You can't add it to your theory of fermions, of smooth fermions, by changing the action, but you can add it to the theory of, you can add it to the effective action. You can add it to the generating functional. If you imagine that you've gotten this this expectation value of j by considering some object like, z of a, which is e to the minus s of eta plus ja. Maybe there's an I here. I guess summed over tau. So if you imagine that you've gotten this j by differentiating an object like this, then this relation tells you that the only way to get the right answer, to get the right finite contact term, is to add this half integer Chern-Simons term to the generating functional. This is not obvious at all. So basically, this says that here you need to add something like plus 1/2 plus 1/2 a d tau, which is ultimately the origin of the Chern-Simons term in this induced action. And it's and the same kind of thing you can actually do in 2+1 dimensions and see that that's how you get the the actual ADA Chern-Simons term. That's one way to phrase everything in a completely finite dimensional way. Like, notice that these objects eta of tau and the underlying Hilbert space for psi everything was completely finite. There was absolutely no divergence anywhere, and yet I was able to show you explicitly what's the step at which you insert the Chern-Simons term, at which the Chern-Simons term is generated, and why you need to have it. And it's only in the context of temporal smoothing that you need to have a Chern-Simons term. Otherwise, if you were to just do everything directly using this kind of canonical calculation, or if you were powerful enough to actually evaluate this integral explicitly without temporal smoothing, everything would be great. You would actually get the right result on the nose. And the same philosophy extends to higher dimensions, and it also explains why you need certain counter terms when you compute partition functions, and so on and so on. These details, various such details, are also collected in the paper, but this is not the final word on this subject. There's some subtleties which I haven't figured out, and so on. But that's one thing that I wanted to stress as something that's relatively novel that comes from this smoothing philosophy. So I will officially stop here. I am happy to take questions. I'm happy to stick around and chat. I have more material, but I definitely do not want to, launch into yet another section without giving everyone a chance to recover. So, but yeah, let me stop here and ask for questions first.
Questions for Djordje?
I was going to ask, maybe you could just say a little bit about this version of Noether's theorem that you mentioned. Just kind of give us an idea of what form that takes, and
Okay, that's perfectly fine. I don't actually have slides for that, but that's but I can describe what's going on there. So the idea is essentially that if you start, so there's like a sort of chain of operations you can do to start from a perfectly nice lattice theory in my context and get something that's a path integral which exhibits continuous symmetries. So basically the logical chain is something like this. So you start from a lattice theory as described in this paper. You smooth. So this is smooth theory still on, you know, a single time slice. So everything is still in the canonical formalism. Then you just do the transfer matrix formalism. So I don't know, let me just call it TM. So you just build the path, like the, let's say the Euclidean path integral in the completely usual way of just stacking things at different times, at the same way it worked for the Berezin path integral just now. And so here, once you're here, so so here you had some fields phi x that lived on just on the space that, you know, so you had some operators which you only had to define by talking about lattice sites on space in space. So here you have some other fields which are now smooth, which very smoothly, but they're still at, you know, completed time at t equals 0. And now here you have some other fields which very smoothly, actually, let me put it like this, which very smoothly in space, but are still separately defined on each time slice. So I haven't performed temporal smoothing yet. And then I can perform, so and let me call this spatial smoothing. So you perform temporal smoothing, and then you get some action, which depends on these variables phi of tau x, which are now your standard path integral variables, and they're really what you implicitly mean when you talk about continuum path integrals. This, of course, forces you to include various counterterms the same way that you needed to in the previous example with fermions, but let's not care about those. The point is that these guys now behave the same way, precisely the way you would like. So they are essentially, they are smooth in both spatial and temporal directions. Well, let me call it D1, let's say, phi tau x, and I should probably put in a d tau here. And by the way, notice that throughout I've kept my lattice spacing to be just equal to 1. The fact that I'm using d tau for the temporal spacing is also not the most crucial thing ever, but I never even had to introduce a label for a lattice spacing to be able to discuss these smooth fields. Okay, so now I get some action which depends on these guys. And the action will just look like something like sum over x and tau, d tau, and then things that look like d phi of x tau, d mu, d mu, blah, blah, blah. Okay, so now the crucial thing, there might be some number here. The crucial thing that I want to stress is that because these fields vary smoothly, you can define a Noether transformation, like you can define the Noether trick, which changes the field not at one point, but at sort of a number of points which are close by. Basically, it doesn't. Basically, if you were to just define this, let's say e to the. Let's say this is a complex field, but it doesn't actually matter. Or yeah, okay. Let's say this is a complex field, and I define something that that depends only on a specific point, x0 and tau 0. So I just define a standard Noetherian trick, Noether trick kind of thing, where I just rotate the phase at one point. If I did that, then I would break my assumption that these guys vary smoothly, and I'm not allowed to do that because the only variables in my path integral are sort of constrained to behave like this. So that means that the Noether trick has to be changed. It's kind of interesting that it turns out that you can define a smoothed version of the Noether trick, where instead of having these delta functions here, you have some smoother transformation associated to these kinds of things. So, which I will not write out because I will get it wrong if I try. But the point is that you get something that is not quite a delta function, but at x and tau, x0 and tau 0, but is instead smoothed like this. On the order of this, and it's smoothed on the order of this ks over n. That's the parameter that controls how smooth it is. Ks over n or ns over n0 in the temporal direction. And it's this guy which then controls how your action varies under this local Noetherian transformation. So basically what I'm saying is that if you define a transformation, even if this is, let's say, pi, this guy here will still be a small number that's of order ks over n. So instead of having an infinitesimal value of alpha, which allows you to define the Noether trick and to write that this guy is equal to the expectation of some current or something like that. Instead of allowing you to relate this guy with something that looks like this, instead of that, you will end up getting this relation, but with this and not O alpha as your small parameter. And this ends up giving you, specifically for the charge conjugation symmetry of the, let's say, free scalar, which just acts as phi goes to minus phi, it gives you the Noether current, which is just phi d mu phi. Which is a total derivative and therefore has a trivial Noether charge. But nevertheless, it actually, this is a crank that you can turn and it spits out a non-trivial current, which is essentially the main thing that Noether would like you to do. And this conjugation symmetry is a completely Z2 symmetry, for instance. And you can do the same thing for parity symmetry and for all the other, familiar Z2 symmetries, for instance. Like I skipped the main parts because I do not want to risk trying to reproduce them now, but they're all in the second part of my paper, like I think the very last section. So, and like it's a very explicit derivation, so you can, it'll take you an afternoon to go through the notation, but yeah, it's very clean. So basically I'm saying that any even finite transformation that's located at a single point, once you smear it to make it consistent with these constraints, it becomes a small transformation, and you can perform the Noether trick, and you can read off the Noether current. Mm-hmm. That's what I'm saying. I do not know what this is useful for, but I think it's still neat. So yeah.
Thanks.
Sorry if this was a very long answer, but yeah, I guess.
That's good.
Again, I think I managed to convey the main idea.
Yeah.
Is your smoothing procedure kind of flexible enough to account for these field configurations which appear in the study of fractons that Seiberg and friends have talked about? Yeah.
In fact, they kind of arrived at something similar. or maybe I should not. Let me just say that I discussed this with Nati, and he is at least aware of this, and he has made some, to me, it would sound like similar comments in one of his papers, like how you define how you end up defining lattice theories, continuum theories by making sure that your fields vary at some. I think he used the phrase macroscopic scale for this KS that I used. So yeah, it's definitely applicable. I think he hasn't gone the full way of applying this machinery to it. Someone could do it, and yeah, I think you would get a even more precise statement about what kind of field theories, continuum field theories, emerge from these fraction theories. So yeah, I would say that it's definitely applicable, and to my knowledge, it hasn't been used yet in that context.
Okay, thanks.
I have a quick question.
Yeah, please.
Could you just remind us, please, like at what point we used the fact that you had to start with a theory that had continuum in time, like going from the lattice theory with continuous time to then like the smooth theory on t equals 0?
At what point did I need to use that? Well, I mean, I was in fact agnostic about time because I was just always being at t equals to 0. So from this canonical perspective, I could always just define time as a parameter in my unitary operator e to the iht, or e to the minus ht, if you will. But
so when you said that like you need a theory with time, like really what you're using is that like you have this Hamiltonian that you can write down. That's kind of like a starting point.
Yeah.
Okay, cool.
So just the standard Hamiltonian formalism, nothing else happening.
Okay, thanks.
Can you give a little more intuition for a type of theory that wouldn't have a complete base, like pre-base or whatever that was, the complete basis that you needed?
You're asking about this pre-continuum basis thing that I mentioned? Okay, well, sorry, can you repeat the question because I may not have heard all of it?
A little more intuition for the types of theories that wouldn't have a pre-continuum basis.
Oh, okay. Well, so I haven't, okay, so I only have very corny examples. A very trivial example is a theory in which the dimension of the Hilbert space is prime. Because then, because by definition, the total dimension of the Hilbert space is the product of these JKs. And I assume that my momentum space is large enough, there are many different JKs. If the dimension is prime, then this is clearly not going to be possible. So this is now an interesting situation where it seems like, in order to be meaningful, to be able to meaningfully talk about a continuum limit, you don't just want the dimension of the Hilbert space to be infinite, you want it to have some structure, some number theoretic structure, to be a product of many slightly smaller numbers. I suspect this is not super crucial, that you can maybe then approximate it as, even if it's prime, that you can kind of approximate it in some way as a large but non-prime number, like a power of 2 or power of something. But I did not study the kinds of corrections that would, the kinds of deviations from the continuum that would induce. They would exist, I just have not studied them. So that's one example. And it's probably the main example. I mean, the other examples would all be theories in which I don't know if these exist, but very, very disordered theories in which you're if you just have no conserved charges that are, in which essentially all these JKs are forced to be essentially 1. So the only conserved operators are the projectors onto the eigenstates. I do not know if this is possible. I mean, I also have not thought about it too hard yet. But if there is a theory in which the only symmetries are projectors to the eigenstates, then this is an example. Yeah, those are like the two main examples that I can think of. But I'm being open-minded that there may be others. But in most uses, we will start with a lattice theory, which is just a product of some local spins or fermions or whatever, or U1 variables or whatever, and then we're kind of guaranteed that the pre-continuum basis will at least exist. The interactions, if the interactions are strong, if these numbers here and here are strong, then you may not have a nice induced topology. And actually, let me finish this thought by circling back to what Mark asked me earlier about gravity. So in particular, I can imagine that these numbers nk and the momentum space do not in any way correspond intuitively to the original lattice on which you've described the theory. So you can have a very strongly interacting theory on some lattice, and it turns out that the let's say on a 4-dimensional lattice, or sorry, 3+1, like 3-dimensional spatial lattice. And then it turns out that the actual momentum space structure that you end up inducing by the Hamiltonian is actually has this matrix, has this space P be a 4-dimensional matrix, a 4-dimensional lattice, not a 3-dimensional lattice. So that would be a trivial example of holography. That would be an example in which you have some very generically strongly interacting lattice theory whose pre-continuum basis and the natural topology in momentum space is described in a higher dimensional theory. String theory is another trivial example of this. If you have a bosonic string, you can think of it as some CFT on the world sheet, which is strongly interacting and so on. But once you go into a basis in which your momentum space is 25 dimensional or something like that, then it looks like free particles, and it looks like it just contains operators like this. So yes, so I think that there are theories in which the relation between the NKs or the momentum space is completely obscure from the starting point, like it lives in a different dimension from the original lattice, etc. But they still exist, and that's sort of the reason why every time we find an example, that's amazing, and that opens up a new area of physics. And this is how I essentially propose to think about this. Basically, every time we find a pre-continuum basis that's like very different from the original theory, then that's a sign of a very non-trivial duality or something like that.
Okay, maybe we should thank Djordje again now.
Thank you. So yeah, if people have